All right, so in the last video, we did an in-depth analysis of this molecular orbital diagram of octahedral complexes, considering that you have 6 ligands that are undergoing only sigma bonding. Later on, we'll get into what happens if you have pi bonding. But we came to a very interesting conclusion, which was that 18 electrons will fill up until you have to put the 19th or 20th electron into an anti-bonding orbital. So that came up with this idea of the 18 electron rule, which says that complexes, transition metal complexes with 18 electrons will be particularly stable. And so this is sort of the equivalent of the octet rule, but for transition metal complexes. So we have to learn now how to count electrons in transition metal complexes. There's 2 ways to do this, and I'll show you one of the ways. The handout that I posted online goes into this in detail. Your book tells you both ways. Okay, I'm just showing you the way that I think is the easiest. So first thing that you need to do is you need to count the number of metals on the you need to count the number of metals in the transition metal, right? And so to do this, all you're going to do is look at the just pulling up the periodic table here. Look at the row in the periodic table that the transition metal is in. So for example, scandium is going to be 3 electrons, titanium is going to be 4. Why is that, right? And then look at the periodic table. Scandium is in group 3, titanium is in group 4. And you may be thinking about, well, do I count these s electrons? And remember that for transition metal complexes, we talked about in the last video, the 4s is actually higher in energy than the 3d. Okay, it doesn't follow the same energy ordering as the periodic table. So all you have to do is say, all right, scandium is in group 3. I'm going to count that as 3 valence electrons. So that's the first step. Second step is just like any Lewis structure business, subtract n number of electrons if the overall complex has n plus charge, or add n electrons if the overall complex has a negative n charge. So you have to account for the charge of the complex. And then you're going to add in electrons that are contributed by the ligands. See the handout for really a detailed analysis of this, but all the examples that I go through here in this video, I'll explain to you how I'm getting the numbers that I do. So let's start with this molybdenum hydride phosphine complex. So what are we going to do? First, we look at the periodic table, and we see that molybdenum is right here beneath chromium. It's in group 6. So we're going to put 6 electrons for molybdenum. Now, there's no charge, so we don't have to do any accommodation there. The 4 hydrides or hydrogens are 1 electron ligands, and the handout goes into detail about this, but the quickest and easiest way to figure out what type of ligand you have is if you have a 1 electron ligand, that's going to be ligands that form molecules that are stable when you add a hydrogen to them. So if HX is a stable molecule where X is your ligand, that's going to be a stable neutral molecule. That's going to be a 1 electron ligand. So in this case, X is hydrogen, right? Because we're evaluating whether or not the hydrogen ligand is stable. And so, that's HH, which is H2. And we know that hydrogen, diatomic hydrogen, is a stable molecule. So that's a quick way to determine that these are 1 electron ligands. We have 4 of them. So we're going to have a total of 4 extra valence electrons there added up. Now for the phosphines, these are just R groups. They could be anything. Phosphines are 2 electron ligands. How do we know that? Well, we draw the Lewis structure out for a phosphine, right? What is that going to look like? That's going to look like this, and there's going to be a lone pair. And adding an H to this molecule isn't going to be a stable species. It would only be a stable species if we did, R3PH plus. And the rule is asking you, without changing the charge, is it stable to evaluate if it's a 1 electron ligand? This is a 2 electron ligand, and it's because of the lone pairs. So ammonia, phosphines, water. These things will be 2 electron ligands because they're going to be donating a lone pair. Okay, at least most of the time, that's how they're going to work. So we have 4 of them, 4 of these phosphines, and so they are 2 electron ligands. They are going to get charge of 8. We'll also go in depth during chapter 8 videos, which you can go to now if you want to, where we talk about all different types of ligands and in organometallic chemistry and how many electrons they are and kind of why and how they work through bonding. But simplified way is 1 electron ligand, HX, stable molecule, lone pair donor is going to be usually a 2 electron ligand. All right, so then we add up the total amount of electrons. We got 6 plus 0 for the charge, 4 plus 8 is 18. So, this is a particularly stable species. It follows the 18 electron rule. What about this example? This is a nickel-allyl complex. So this, right, is an aromatic system. That's shorthand for this, right? And this allyl ligand has 2 resonance structures. So these are resonance structures, right? So again, we look at the periodic table. Nickel is right here. Okay, it's in group 10, so it has 10 valence electrons. And then we need to, we don't have any charge. Okay, and we have 2 allyl groups. These are 3 electron ligands. Why are these 3 electron ligands? Well, double bonds a lot of times will act as sort of a lone pair. There's 2 electrons in that pi bond. So you're getting 2 electrons from the pi bond. Okay, and then remember, HX, is HX a stable molecule? Yes, HX would be a stable molecule, right? Because what is this allyl business? This is CH2 minus, basically, right? There's a CH2 minus group here. So if you were to add another hydrogen here, that would then get rid of this minus charge, and it would be neutral, and it would be a stable molecule. Okay, so HX definitely is a stable molecule here. And so that gets you your other 1 electron. Okay, so total for the allyl ligand is 3 electrons. There aren't so many examples of the different types of ligands that there are, or a lot of them follow the same patterns. So again, if you look at that handout or the later lecture videos, you'll be able to see, how to count these very easily. But this is the general idea. So this has 16 electrons. Okay, now it turns out that a lot of this is a square planar complex, and it's a D8 metal. Why is this a D8 metal? Let's talk about D electron count. That's another thing we should go over. Okay, D electron count and also oxidation state. What would the oxidation state of this be? Well, this is a -1 ligand. This is -1 ligand. The overall charge is 0, so this is nickel 2 plus. And if it's nickel 2 plus, okay, then the D electron count for this is going to be 8, right? It's going to be a D8 complex, okay, because we had 10 electrons and we removed 2. So this is going to be, and I'll ask you about this in the homework, this is going to be a nickel 2 species, and it's going to be D8, okay? Now, you'll notice this violates the 18 electron rule. There's actually 16 electrons. This is very common for D8 complexes. Why is that? Well, if you go back to our square planar complex, okay, you may remember that there's this very high B1G orbital, this dx squared minus y squared orbital. It's really, really anti-bonding. We can go back even further, right, and look at the crystal field splitting slide, where we had here a square planar. Look at that. I mean, it's 12.28, and the other ones, this is a little destabilized, but not much. The other ones are stabilized. So you really don't want to put those extra 2 electrons up there. And so as a result, some people say there's a 16 electron rule for square planar complexes. You can call it that if you want, or it's an exception. All right, so let's go back. So we did the oxidation state of this one for this nickel group. Let's go back, since I forgot to talk about it for this molybdenum one. So H, right? This is a H, formerly a H minus ligand, okay? And again, remember HH, that was a neutral ligand. That's how we figured out this was a 1 electron ligand. So neutral stable molecule. So we have 4 of these -1 charges, okay? We have kind of a 4 minus there. And then phosphine, well, that's a neutral molecule just by itself, right? Phosphine is a neutral molecule. So that's not charged. The whole thing is is neutral. So that means molybdenum has to be +4. So we're going to have molybdenum in its 4th oxidation state. And then if I were to ask you, what's the d electron count? Well, the d electron count is, okay, well, it's in the 4th oxidation state, right? So we have 6 valence electrons from molybdenum. Now we removed 4 because it's the 4th oxidation state. So we're going to be a D2 complex, right? And if we're D2, I could further ask you, what is the splitting diagram if this was octahedral? Now, this isn't octahedral, okay, so maybe that's not the best example. This is 8 coordinate. But if it was octahedral, what would the splitting diagram be for a octahedral complex? Well, we could write, we know this, e.g. T2G, okay, and then we're going to populate 2 electrons, spin unpaired for Hund's rule in the e.g. orbital. Let's keep going. So this cobalt complex here, we're going to first look at our periodic table. Cobalt's in group 9. All right, so in group 9, we do have a charge, and so that's going to be, it's plus charge, plus 1 charge, so we have to subtract out 1 electron. And then we have 2 of these cyclopentadienyl ligands. Those are 5 electron ligands. Why? Well, cyclopentadienyl looks like this, okay? And there's a minus charge there. This whole thing's aromatic. Again, you can look at, wait until the organometallic lecture videos to really dive into this. But for electron counting purposes, you have 2 electrons for the double bond, okay? It's kind of acting like a lone pair. There's 2 electrons in the pi system there, 2 electrons for this double bond, and this is a minus charge. So that's going to be 1 electron. Again, because HX, where X is this whole anion, is a stable neutral molecule. So we got 2 plus 2 plus 1 gives you 5. So we have 2 of these 5 electron ligands. That's worth 10. Total is going to be 18. This follows the 18 electron rule. And so if we dive into this a little bit more, we can figure out what the oxidation state is. Let's see. So we have a -1 ligand here, a -1 ligand here, and the whole thing is plus charge. So that means cobalt is going to have a 3+ in order for the whole thing to be a plus charge. So we're going to have cobalt 3. And how many d electrons is that going to have? Well, cobalt was in group 9. We removed 3 of those electrons. So that's going to be a D6 configuration. All right, so let's stop it there, and then we'll go into some different trends that happen as you move across the periodic table because of the 18th electron.